Hello everyone, my name is Parsa, and in this video I'll be covering Cauchy Euler equations. These equations are often encountered in various applications of physics and engineering, and they provide some unique challenges in solving ordinary differential equations, or ODEs for short. This topic is covered in MAT2150, Differential Equations in Matrix Algebra. I'm currently taking the course, and I thought I might make a video on a topic we covered in class so I could help other students out. If you have any questions at any point in this video, and you see me on campus or walking out and about, just walk up to me and ask away. I'm more than happy to answer any question you might have. Anyway, let's dive right in. So what exactly is a Cauchy Euler equation? Cauchy Euler equations are a specific type of linear homogeneous ordinary differential equation. This is the form of a second order Cauchy Euler equation. It's called second order since the highest derivative of the function is the second derivative. It's called linear because the differential equation is defined by a linear polynomial. And it's called homogeneous because in the case of linear differential equations, the right-hand side is 0. You can generalize the form to higher order ODEs, but for sake of simplicity, we'll stick to second order only for the meantime. As an aside, x is specified to be greater than 0 because when you divide by ax squared, the y prime and y coefficients will be divided by x and x squared respectively. So x equals 0 is a singular point for that equation. So how exactly do you solve a Cauchy Euler equation? A common technique when it comes to solving for differential equations is to make an educated guess. Based on the structure of the equation, you may be able to guess the appropriate form of the equation, which in this case is x to the power of r. Later on, we'll show how to derive this form using a change of coordinates, but for now, we'll assume we already know the form of the equation. As you can see, x to the r is a solution to the equation if and only if ar squared plus b minus ar plus c equals 0. The equation below involving r is called the characteristic equation. In this case, it is a quadratic equation, and you can find the two solutions using the quadratic formula. However, if the characteristic equation has repeated roots, that means one root that's repeated twice in the second order case, you'll have to know the following result. The other solution will be of the form x to the r times ln x. This will be clearer why this is the case when we look at the coordinate transformation later. For now, we just need to know that this is a special case to handle when it comes to repeated roots. If you have complex roots, you can use the following formula. This formula will include sines and cosines of ln x multiplied by x to the r. This formula can be derived using Euler's formula and some basic algebra. Now, let's cover an example and see how this works out in practice. Here we have 4x squared y double prime of x minus 4x y prime of x plus 8y of x equals 0. Here's the characteristic equation, 4r squared minus 8r plus 8, which can be factored into 4 times r minus 1 times r minus 2. As you can see, 1 and 2 are the roots of the characteristic equation and form the solutions that we'll see later on in the next slide. Therefore, both x and x squared are candidate solutions. And since Cauchy Euler equations are linear, the linear combination of the two will form the general solution. Therefore, c1 times x plus c2 times x squared is the general solution to this Cauchy Euler equation. If you want to find the specific solutions, we'll need to find the appropriate values of c1 and c2 such that they satisfy the initial values given. However, in this case, since we don't have any initial values, we'll leave c1 and c2 undefined. Now let's go ahead and cover another example. Here we have 5x squared y double prime of x minus 5x y prime of x plus 10 y of x equals 0. Here's the characteristic equation for the Cauchy Euler equation. 5r squared minus 10r plus 10, which can be factored into 5 times r minus 1 minus I times r minus 1 plus I. As you can see, 1 minus I and 1 plus I are the roots of the characteristic equation. Therefore, both x cosine ln x and x sine ln x are candidate solutions. And since Cauchy Euler equations are linear, the linear combination of the two will form the general solution. Therefore, c1x cosine ln x plus c2x sine ln x is the general solution, and we've solved the equation. Let's cover one more example. Here we have 9x squared y double prime of x plus 3x y prime of x plus y of x equals 0. Here, the characteristic equation is 9r squared minus 6r plus 1, which can be factored into 9 times r minus 1/3 squared. As you can see, 1/3 is a repeated root for this Cauchy Euler equation. Therefore, both the cube root of x and the cube root of x times ln x are both candidate solutions. And since the Cauchy Euler equations are linear, the linear combination of the two will form the general solution. Therefore, c1 times the cube root of x plus c2 times the cube root of x ln x is the general solution. Now let's take a look at higher order Cauchy Euler equations. In this case, order 3. This is their form. We now have an x cubed y triple prime term, and this generalizes further to higher orders. This is the formula for the form of higher order Cauchy Euler equations. The a sub k's are sequences of constants, and the y to the k term is the kth derivative of y. As you can see, the form is actually very simple when expressed in this form. Now let's go ahead and talk about coordinate transformations. The key coordinate transformation to make sense of Cauchy Euler equations is the following: x equals e to the t. This coordinate transformation will transform Cauchy Euler equations to constant coefficient linear differential equations. This change of coordinates explains why x to the r ln x is a solution to the repeated roots Cauchy Euler equation. Namely, t times e to the rt is a solution to the repeated roots constant coefficient linear differential equation. When you change coordinates, you get x to the r ln x, which is consistent with what we showed earlier. You could also use other techniques to find the solutions to the Cauchy Euler equations, but this coordinate transformation was particularly enlightening to me. Another way to understand Cauchy Euler equations involves differential operators. We can define a differential operator L to be x squared times the second derivative with respect to x plus b times x times the derivative with respect to x plus c. You can factor the differential operator into two terms and take the inverse of each one to solve for y. The two resulting differential equations are easy enough to solve, and they'll coincide with the results we derived earlier. Now, let's go ahead and cover a more advanced example. Here we have a third order Cauchy Euler equation. The equation is 2x cubed y triple prime of x minus 6x squared y double prime of x plus 14x y prime plus 16y of x equals 0. Here we have the characteristic equation. 2r cubed minus 12r squared plus 24r plus 16, which factors into 2 times r minus 2 cubed. As we can see, 2 is a repeated root with multiplicity 3. In this case, we'll have an additional x squared ln x squared term. Therefore, x squared ln x, and x squared ln x squared are all candidate solutions to this Cauchy Euler equation. And since Cauchy Euler equations are linear, the linear combination of the solutions will form the general solution. Therefore, c1 x squared plus c2 x squared ln x plus c3 x squared ln x squared is the general solution. Now let's cover another advanced example. This time we also have a third order Cauchy Euler equation. The equation is x cubed y triple prime of x minus 6x squared y double prime of x plus 18x y prime of x minus 24y of x equals 0. Here we have the characteristic equation. R cubed minus 9r squared plus 26r minus 24, which factors into r minus 2 times r minus 3 times r minus 4. As we can see, 2, 3, and 4 are roots of the characteristic equation. That means that the solutions will be of the form x squared, x cubed, and x to the fourth power. Therefore, x squared, x cubed, and x to the fourth power are all candidate solutions to this Cauchy Euler equation. And since Cauchy Euler equations are linear, the linear combination of the solutions will form the general solution. Therefore, c1 x squared plus c2 x cubed plus c3 x to the fourth power is the general solution. Let's cover just one more advanced example. This time, we have a fourth order Cauchy Euler equation. The equation is x to the fourth power y quadruple prime of x minus 2x cubed y triple prime of x plus 51x squared y double prime of x plus 21x y prime of x plus 25y of x equals 0. Here we have the characteristic equation, r to the fourth power minus 8r cubed plus 26r squared minus 40r plus 25, which factors into r minus 2 minus I squared times r minus 2 plus I squared. As we can see, 2 minus I and 2 plus I are repeated roots of the characteristic equation with multiplicity 2. That means that the solutions will be of the form x squared cosine ln x squared sine ln x squared ln x times cosine ln x, and x squared ln x sine ln x. Therefore, x squared cosine ln x squared sine ln x squared ln x cosine ln x, and x squared ln x sine ln x are all candidate solutions to this Cauchy Euler equation. And since Cauchy Euler equations are linear, the linear combination of the solutions will form the general solution. Therefore, c1 x squared cosine ln x plus c2 x squared sine ln x plus c3 x squared ln x cosine ln x and c4 x squared ln x sine ln x is the general solution. Now that's the end of the video. I hope this more detailed explanation of Cauchy Euler equations has helped you understand their structure, methods for solving them, and how they arise in various contexts. Thank you so much for watching, and don't hesitate to ask any question if you need further clarification. Have a wonderful day.